Sunday.
Okay, yeah.
Oh, I see this recording has started thing. I think I will start. Oh, all right. The clock just jumped to 12 p.m. U.S. Central. So I will start this session as we planned. So hello, everyone. First of all, welcome to the session, Education and Training. It is a XCC, Software Engineering Education and Training. So thank you very much for joining us. So in our session, we have 4 really interesting presentations. So the way it will happen is we'll first have the 4 presentations together. Then after that, we'll have like a Q&A all together. So during the presentations, please feel free to type any questions you want to ask in the channel, but we will prefer you to point it to the name of the presenter, so we will immediately see who you want to talk to about this questions. So first one, presentation is about the paper Seeking Flow from Fine-Grained Log Data. The presenter is Patri Ihantola. So Patri, please share your screen and start your presentation.
Thank you, Yu. Hopefully I'm now able to make it to a slideshow. Okay, so this is a joint work with Benjamin Coley, Arto Hellas, Juho Leinonen, and Michiel Spape, all from the University of Helsinki. Briefly about the background. So if we look about how flow experience, stress, or emotions in general are measured in software engineering, so most of that is based on intrusive methods. It's typically measured with questionnaires. The measurements can be augmented with physiological indicators such as heart rate variance, EDM, muscular tension, and so on. But in any case, how we are measuring that's quite intrusive. And these approaches are good for research, but not really for long-term monitoring of our behavior. However, there's some research related to typing patterns and mouse usage, and this Agetta's review is quite good article. I could recommend that one. That the way how we type can also be used to predict some basic emotions, like and how the typing is measured. There are many approaches for that. It can be like typing force or typing patterns like degraphs between key pairs and so on. And in the context of programming education, on the other hand, the same typing patterns have been used to detect the difficulty of software development and to detect the programmers' existing knowledge and performance in given tasks. And now if we think about what the flow really is, so then as that's the balance between the challenge and skill, our main proposal in this paper is that it should be possible to predict the flow with the just with the typing data or with the mouse usage data. And this is the main idea in this paper. We have some preliminary ideas there, like first how to model stress, like when we are kind of so we kind of would like to create a machine-based approach, machine learning-based approach where we collect some baseline for the flow experience or stress by using questionnaires and physiological measurements. And then we kind of collect the typing behavior and try to create the mapping or prediction from that typing behavior to the experienced flow. And we did a brief case study to get towards this objective, and we investigated what's the relation between log data-based features and student-reported affective metrics, including focus on the task, and what is the relationship between educational value, assignment difficulty, and focus on task. And this small case study was based on about 3,000 students who were solving programming exercises in our learning environment, which is essentially an augmented NetBeans IDE. And these 3,000 students solved there like 170,000 programming exercises, and after each task, they evaluated the educational value of the task, difficulty of the task, and how focused they were when solving the task. And briefly about what we found, so we looked like different measures there, like that how many code insert events there were, how many code remove events there were, how many times the project was executed, how many times the window was changed there, and so on. And they are kind of for the difficulty, there are kind of small correlations, but I think that what we can find here is that in many cases the correlations are rather small, and I think that the difficulty is here something what we can kind of at some level predict, but that again is still something what we need to work on in the future. And then if we look at this educational value, assignment difficulty, and how focused the person was when solving the exercises, so the correlations are here. And then we wanted to investigate a bit more these relations, and I think that I would just leave it as it is here without trying to give an explanation. I hope that in the QA section you would be able to give me an explanations here, but at least it looks like that if persons feel that they are really focused, then the connection between the assignment difficulty and the educational value is a kind of more linear. And if a person feels that it is not that focused on solving the task, then the difficulty and the educational value are kind of the connection is not that linear anymore, and kind of more difficult the task gets, then more and more kind of less educational the exercise goes there as well. But I think that was my kind of 5 minutes here. I hope to get good questions and even more good answers to my questions. Thank you.
Yeah, thank you, Patrick. Yeah, definitely, everyone. If you have any questions for Patrick, please feel free, either ask them in the Q&A in person or just type them in the channel here. Yeah, so yeah, that's our first presentation, everyone. Next is our second presentation. It's about the paper, Write a Line, Test with Answer Templates and String Compilation Hints for Self-Learning in a CS1 course. Our presenter is Oleg Sichev. Oleg, please start sharing your screen, please.
Yeah, can you see my screen?
Yes, that works fine.
Yeah. So today I will tell you about our experience with implementing equations regarding writing a single line of code and using regular expressions as a templating mechanism. The questions about writing a single line of code bridge an important gap between theoretical knowledge and writing complex programs. They let students who struggle with learning to have some practice before they encounter really difficult tasks. There are different approaches to code writing exercises, but for line writing questions, we selected pattern matching. First, because it has very high tolerance to errors in the answer, because it can provide string completion hints that can tell the students how to fix any answer regardless of how wrong it is. And it also requires moderate amount of effort to create tests and tasks because we don't have to list all variants if your pattern have several variable paths. We developed a module for popular Moodle LMS Perec module which matches student responses to Perl-compatible regular expressions, shows the correct beginning of a partially correct answers and the incorrect part, and generate shorter string completion so it can give hints, next correct character and next current token if the student is stuck without consulting teachers. How it was organized in the course. We had 6 lab assignments for developing a program. Before doing every assignment, students should have passed a topic summative quiz. In order to prepare for them, they were provided with formative quizzes that they could do during homework. There were three kinds of formative quizzes: regular quizzes, perec, and correct writing, our and other questions. As a part of their final exam, they passed exam quiz to have all the knowledge for the entire semester. They used the same question bank with the topic quizzes, so the same formative quizzes could be used to prepare for them, but it was voluntary. We created more than 700 of regular expression questions and measured the effect during 4 years with almost 500 students. What did we learn? Teachers created efforts for some easy answers, but also for some very complex answers, up to 70 tokens and up to 18 different paths throughout the same expression. Listing all 18 variants is a problem. Students sometimes give up to 30 unique answers on regular expressions. The most important problem was handling extra parentheses that regular expressions cannot match, but introducing recursive subpattern features and special syntax to improve readability of expressions. We raised recall to 99% and F-measure even higher, and these are really good results for variable matching. As for how students used those questions, we can see that 80% of attempts during homeworks ended in correct answers, and about 1/3 of them used hints. So students could find hints most of the times and solve the task without a teacher. But more than 10% of attempts didn't result in a correct answer, and sadly some of those students used hints but didn't use them to the completion. Of all students, about half of them preferred to use correct formative quizzes, and from 6 quizzes they made on the average 9 attempts during semester. Some very little amount of students were able to answer any question at all, and some preferred to just see the questions without even trying to answer them. So what can we conclude? Regular expressions is a viable way to implement short open answer programming questions like writing a single line of code. String completion hints provide a note feedback to let students train on their own during homework, and our best advantage was that teachers and TAs spend a lot less time answering students' questions about their quizzes at home, so that the classroom time was freed for better works. Because string completion quiz helped to fix even some very wrong answers that would have posed problems for other methods. But students who used hints too often were performing poorly, and so it can be predicted that the student needs more attention. Our model is published in Moodle plugin database under general public license. It's openly available for you, and we will be glad to receive feedback. Thank you.
Thank you, Oleg. Very interesting. And also thank you for sharing us with the link of your work. Yes, so everyone, our next presentation, the third paper is ASPA, a static analyzer to support learning and continuous feedback on programming courses and empirical validation. So our presenter is Roope Luukkainen. So please, Roope, yeah, we can see your screen. Please go ahead.
Okay, hello everyone. I'm Roope Luukkainen and I will present our paper. And introduction to this study is very shortly that we empirically validated a tool called ASPA, which is a static analyzer which gives feedback for students when they run their programming assignments with it. And we use it in LUT University CS1 programming course, which is lectured with Python 3. So this only works currently with Python 3. And our research questions are as follows: which is the attitude toward using ASPA? Which is the perceived ease of use of ASPA? Which is the perceived usefulness of ASPA? And I will go through what we found based on each of these questions. So this attitude, we had 2 surveys, the background survey and this main survey at the end. The background survey was at the beginning And in this feedback survey, we got 236 answers, which is 46% of all students. And out of these students, 205 used ASPA and 31 did not use it. And out of those, 10 did not use because they felt that they do not need help doing the assignments. So they probably had some prior programming knowledge. And then how much they use it in course project, the students mentioned that they used ASPA like this. So many times was the most common answer, and 2 to 3 times was the second most. So we can say that over like 80, almost 90% used ASPA at least 2 times in course project. And in weekly assignments, the possible answers was from 0 to 36, and that's because we introduced ASPA after we introduced functions in our course. So it was on week 5 and actually week 4. And that's why there is not all the assignments which were possible to analyze with ASPA, but some students did analyze all of these 36, and some of analyzed only like, well, none. But on average, they analyzed almost 11 assignments with ASPA. So students did use ASPA, at least they mentioned that they did use it. And then this second question was this perceived ease of use. So how students felt using ASPA, was it easy or not? So if we think that students have this very simple code, they open ASPA and select file via GUI, and then they select which analysis they want to use. Basically, they should select all of them after the half point of the course. So almost every time they use all of them. And then they execute analysis, and then ASPA shows what it detects. So in this very simple example, it shows that there is a global list, and students should fix it because that's a big violation in our course. So very simple workflow here, and students found it also very easy. So selecting these detections, which means selecting those analyses on the left-hand side, was the easiest one. It was 4.5 on average, and in Likert scale from 0 to 5. And selecting files was 4.4, and understanding results was also 4.4. And as we can see from the table with the exact numbers, there are most of the answers are easy and very easy, so that explains why it's so high, these averages. And then the maybe most interesting thing, was it actually useful, or did students feel that ASPA was useful tool? These are just highlights I selected. So there were like 10 things in this question 7, and more categories in those open field questions, which were questions from 8 to 11. So in this question 7, the students felt that the course would be more difficult without ASPA. It was over 3.5, so 3.7. And also in weekly assignments, they felt same, that ASPA helped them there on average 3.7. And in course project, it was as high as 4.4, which I think it's very high number. And same thing can be seen in the bottom table, that in open field questions, when they were categorized and coded and categorized those codes, the usefulness in course project was explicitly mentioned 81 times. So it's like over a third of students. and the careless mistakes, that helping fix careless mistakes, was the second common, 47, and then general benefit was third common, 39 times mentioned. It means that they said that ASPA was a useful tool, but they didn't explain how. So you could argue, and I think I can argue, that ASPA was perceived as a useful tool by students. And then, even though it wasn't our main part of the study, we did calculate, was there any correlation between downloading ASPA and the grade. And these numbers are downloading ASPA, not using ASPA, because they come from different systems, and we were not able to combine these. So on whole course, when we get all the students and all the grades, also those who did not pass the course, there is very significant difference from between those who used ASPA, downloaded ASPA, and those who did not download ASPA. But I think that's not so meaningful, because there are also students who did basically nothing, which include that they did not download ASPA. And then those who passed the course, the bottom part of the table, it's the most significant was with final grade, and the lowest significance was with examination, which can somehow be or I could think that it's because they were able to use ASPA in weekly assignments and in course project, but in examination they did not have access to ASPA tool, so that might be the case here. But this is one of the future studies we need to do, that what is behind these numbers. But this study was mainly focusing on the perceived usefulness and easy to use, and I think students felt that ASPA was useful tool, so that was a good result. So that's it, and thank you everyone for listening.
Thank you, Rupi. That's really interesting. I'm sure we can have a lot of discussion on that in the Q&A session. Everyone, now we have our last presentation, the fourth paper, that is preparing software engineers to develop robot systems. Our presenter is Carl Hildbrand. Carl, please.
All right, thank you so much. Can you see my screen?
Yes,
right.
Perfect.
That's a yes. Sorry, I can't see anything right now, but I'll start. So hi, and thank you for coming to our talk on preparing software engineers to develop robot systems. But before we begin, if there's one takeaway from this talk, it's that everything we spoke about today can be found on our website at this link and QR code shown now. So let's begin. Robotics as a field has grown steadily over the last 2 decades. And even with all this, the robotics industry is still projected to grow by 25% between 2020 and 2025. So how are we preparing to fill the need for engineers capable of allowing such development? To fill this gap, several curriculums have been developed, and in general, we can fit these curriculums into one of 4 categories. There are specialized graduate level courses that generally focus on specific elements of the robotic system. However, they tend to overlook the fact that robotics heavily relies on software. Next, there are cyber-physical or embedded system courses, which tend to focus on particular aspects of the robotic system pipeline. Then there are massive open online courses that scale up the number of students introduced to these topics. However, they aim for a breadth of student applicants, meaning that graduates may lack in other fundamental software engineering principles. And then finally, we have traditional software engineering courses, which fail to handle aspects specific to robotic systems. With this in mind, we set out about creating a new course. Our goal was to develop a course that would enable upper-level undergraduate students to gain expertise on foundational aspects for robotics. Specifically, we wanted to develop a course that introduces students to robotics while reinforcing the principles of software engineering to better prepare students to develop robot systems. To achieve this goal and develop the course, we came up with 5 guiding principles, which resulted in a set of innovations. Due to the time constraints, we don't have time to discuss them in this talk, but we highly encourage anyone interested to take a look at either our paper or longer talk. To get a sense of this course, let's take a look at an example of both an example lecture and lab, starting with the lecture. The aim of this lecture is to introduce the fundamental concepts related to robotics architecture, robot state, and environment. We start by highlighting how cyber systems differ from robotic systems. We then dig a little deeper and talk about what are the typical states in a robot system and different parts of the robotic systems, for example, path planning and perception. We again go even deeper and start to discuss domain-specific architectures, for example, probabilistic versus reactive control. We then talk about how to realize these systems, realize these real systems, and discuss the different realizations. And finally, we dig even deeper and start to discuss how we would actually implement this using code. For example, using finite state machines to represent the different states that we learned about. Next, let's take you through an example lab. The lab starts highlighting how what we learned in class can be used to implement real systems. We then ask students to implement a basic two-state finite state machine, and this allows students to start feeling more comfortable with the concepts taught in the lecture while not becoming overwhelmed. We then highlight how students can debug their code, and this allows students to self-debug their finite state machines, making sure it works as intended while learning good debugging principles. We use checkpoints to allow students to reflect as well as discuss what they have done with either their instructor or one of the teaching assistants. We then emphasize how certain design attributes should be parameterizable and how students should design code to be easily reusable. With that in mind, we ask students to add an additional state to the finite state machine to verify some input given to our drone simulation. The verification is done using parameterizable constraints, allowing students to demonstrate code reuse and flexibility. We then showcase how testing can be done through simulation, which is something that is extensively done in robotics. To increase the students' breadth and perspective, two additional issues were focused on during the course. First, the class is aimed at upper-level undergraduate students, and thus many are starting to consider positions in industry. For this reason, we invited a guest speaker from industry to speak and interact with the class. Next, as robotics grows and becomes more apparent in our lives, there will be several ethical questions that need answering and considering when developing these systems. We added a lab where students would debate over these issues. In retrospect, we discovered several things that worked well as that need improvement. We'll not discuss all of them due to time, but if we had to highlight one, it's that pairing software engineering topics with robotics concepts is extremely useful, as students learn and reinforce both ideas, while we as educators can use one as a vessel to teach the other. However, on the downside, this requires constant updating as both fields are advancing rapidly. Overall, we feel like this course was a success. In the future, we aim to empirically test how successful this course was. However, we do believe it's currently having impact. Last year, we had 26 students. This year, we have 75. Of the last year's 26 students, 4 ended up in the robotics industry. And additionally, we had several students that emailed us and thanked us for how they actually in their course while talking with the companies that ended up hiring them. So in conclusion, we introduced a course aiming at equipping students with a unique understanding of the challenges in developing the software underlying robotic systems and a set of tools to address those challenges. And with that, thank you for coming to our talk, and remember that everything that we spoke about today can be found on our class website, which can be accessed using the QR code on the left. Thank you.
Thank you so much, Carl. Very interesting. So first of all, I want to, give like a virtual clap to all of our presenters. It's a really, really interesting. And I'm so glad in our session, our 4 presentations covers all the way from CS1 courses to a higher level software engineering class. It's really nice. I also see there's a lot of, interesting discussion going on in the chat channel. So yeah, feel free to type your question there. I will read it out, or you can just, turn on your mic and jump in with your questions. So I see that. So our audience pasted some questions here. For example, the first one asking Patrick about the applications of the work. I think that's quite interesting. Patrick, I know you have already typed something. Do you want to turn on your mic, talk a little bit more about that for this kind of flow detection and analysis? What can we do?
Yeah, I think that all of you could answer that one as good as I am, but well, I guess the obvious use case would be something like hiding the notifications and so on if the user would be experiencing flow. But on the other hand, I think that in the long run, it would be more interesting to understand what kinds of series of programming-related tasks in a professional programming also could lead into a flow experience, like, because I like that if there typical workday, that's a kind of, you may do some code reviews, you may do some programming, there might be some other tasks what you are doing, and then if we would understand how those different activities would be in the best way provided for a person. So I think that kind of research would be really interesting in the future. But of course, at the moment, our prediction is so lousy. So I think that this is something that we should first have a proper prediction. But there are kind of, if we are just looking at the basic emotions, then those predictions, like state-of-the-art predictions, those are actually pretty accurate. And then I would not take too strong conclusions from our small case study there, because that was just kind of experimenting a bit. And the main idea was there to give the idea, not the study.
Oleg, do you have a follow-up question? Please.
But actually, Petri, it's a very measuring the flow. It's very interesting topic for interactive intelligent learning system. When the system selects adaptively the next questions, then learning if the student was bored, or if the student was stuck, or if the student goes with the flow. It's a very important topic. So if you have something that can be practically used, we will be glad to collaborate and use it, or we can think about several research. I can write you my mail, or you can find it in the article. Yeah,
Please,
if you're interested in working on that, we concentrate on domain modeling in our recent work, but we would be glad to have something that can watch students and measure students' affectional state without been distracted to develop this part ourselves. It's a topic that always bothers me in the system. Are we offering them too easy tasks, or are we offering them too hard tasks? And for now, we have only the kind of errors they did, but measuring emotional state might be also good.
Yeah, so I may ask a follow-up question representing maybe the audience who do not have a lot of background on flow state, this kind of psychology concepts. I wonder, since a flow is like, defined as a state, which means that the term of it can be relatively short compared to traits, right? Like a depression or anxiety. I wonder, how would you suggest that other researchers, if they want to measure flow state, how long or how complicated the task should be so we can actually observe the change on the flow? Or it's like
That's a
an
really
instant.
that's a really good question, and I'm not able to kind of give a kind of a really good answer there. But when we were looking at the correlations between some variables, so we derived some features based on session length, like that, and there we kind of looked, for example, how many programming exercises a student solved in the previous session, assuming that there were no longer breaks in that session than 1 minute, 5 minutes, or 10 minutes. And there, I think that the 5 minutes break point was the kind of the one that worked best. So I would kind of assume that for flow, I think that I'm just hand waving here, so feeling bad. But it would be shorter there, but yeah.
Yeah, maybe it's like useful for the researchers first to conduct like a pilot study, right, to see if that works. Yeah. All right. Yeah, so I see that Carl, you have a really interesting. I actually have the same question for Oleg. Carl, do you want to kind of state it again so our audience can easily understand the discussion?
Yeah, I already answered a bit of it in the chat. It's really, if you open the paper, I can just say everything in just 5 minutes. We found that the student who had lesser knowledge benefited more, because writing a line is not something really good students struggle with. It's more for students who had problems with language syntax, and especially, for example, we've had questions that has always a lot of problems when students have to call a function and use an array, pass an array or a part of a multidimensional array, and the number of square brackets is a total killer for a lot of students. And when they use it, are provided with training quizzes and that can tell them the right solution, they try and they learn from trying. I observed just this behavior when they can't get the ruler from textbooks, they sometimes can get with experimenting with our system, but this needs timely feedback. If they have to wait for teachers' attentions each time they stuck, it doesn't work. When they can see next and correct solution on themselves, it works a lot better. For well-learning students, they need more high-level exercises.
Yeah, so Carol's question was basically asking Oleg, does the tool work similarly between, or differently between the good students and the students who struggle a little bit more? Yeah, thank you, Oleg, for your question. I actually have a question relevant to the work and maybe a question for everyone in our session. So, as like educators, when we teach students when they're stuck, we definitely want to give them some hints to help them to move forward. However, we don't want to give them too many hints so they don't have a chance to think through the problem themselves. So I wonder, Oleg, for example, when you design such tools, how do you kind of balance the need here?
Well, actually, in this tool, as you can see, first of all, as we get, it's an experience report of many years of using it, so it's not really rocket science. It was implemented years ago. In this tool, we implemented simple settings. For example, teachers can drop grades for each using of hints and lower the grades for the quiz and so on, and the number of hints can be limited. But what we are working now is providing not completion hint but semantic hints. It's already entirely different products with a lot of closet answer questions, but with a lot of variants, and they analyze it using reasoners, using artificial intelligence techniques, modeling the correct lines of reasoning for students. And what we found, and what I actually want to learn to do and working towards it, but I don't have exact term in English. We have entirely different pedagogy here. Sometimes as a teacher, and I think this is sometimes is the best practice, when I have time, I ask the student is stuck, I ask him a series of simple questions about the things that he must think to solve the task. We call them leading questions. Sometimes I thought the term follow-up questions, so it's not. And they make students think and recall, and it often lead to, wow, I understood. And it's often better than hints. And for now, but I didn't see if anyone can point me to a pedagogy literature in English about such kinds of questions. I would be very grateful, because I wasn't able to find anything of small questions. And for now, I'm working on modeling the required thinking for students, decision trees to solve a task, and modeling sequences of small questions that help students think, because it's a lot more promising interactions than just saying, oh, you didn't this is wrong, you must do this. The question stimulates thinking, while hinting is better than nothing, because when students have to wait for a day or a week before they can ask a teacher, it was completely awful.
Mhm.
With those small hints, we also have, I reported it like correct writing questions. I maintain it. They use it longest common subsequence algorithm. They can tell if a token is misplaced. So student puts a function here wrongly, and it says, oh, your function name is misplaced. It actually impresses students and helped them to learn syntax. We experiment with different kind of hints, but for now we are working with semantic hints, like student is asked the order of evaluation and then saying, oh no, this operator cannot be evaluated right now because there is an operator with higher precedence or the same precedence and left associativity to the left of it or some other law. And we are working in this direction right now, but this I mostly report on conference like ITS, Intelligent Tutoring System, ICALT. For now I was rejected at IET, but we are working towards there. And if everyone is interested,
Yeah.
then you
Yeah.
can contact me.
Yeah, you mentioned IDE. That's really interesting because I see in the chat, Carl has a similar question about integrating Arupe's work in IDE. So yeah, Carl, do you want to just ask him in person, like Arupe?
Sure.
Carl, yeah.
So I was curious when you were discussing the static analysis tool. When we talked with our students, we encouraged them to go down a kind of a certain set of IDEs and a certain I guess path that was kind of standardized, but and that would definitely help because now your tool only needs to work on one set of IDEs. But I was curious, like if we wanted to integrate your tool into our tool chain, is it how easy is it to kind of move between different IDEs, different environments, things like that?
Yeah, well, currently ASPA tool is like standalone tool, which is like given students as a single file, but that's like that's like a proof of concept version. So we are planning to integrate it our submission platform, which auto grades those weekly assignments. But we are also like thinking integrating it to IDE. So we have not like we have not decided which way to go, or should we do both, but it's like we are planning to do something else than providing a like extra tool for students, because it's so much more convenient if it's integrated to IDE or submission platform. And like you said in the questions, some of those questions, I wasn't sure was it this question or other question, but some of these can be done on the fly. And for example, PyLint does similar, some of the like these violation detections are similar to PyLint, but ASPA has like specific for our course and our style guide. They could be changed, but for now only via changing the programming code. So there is not yet interface to calibrate those. Well, the error message can be calibrated, and you can like ignore some violations. But if you want to add or modify violations, you need to do it still via source code, which is well inconvenient for now. But well, static analysis is with AST3. AST is simple detections are very fast to make. Hard part is to give the like updated version of the tool for students if it's not integrated anywhere. So that's like the harder part.
I think though, when you said it was a standalone tool, that's kind of nice because that it means it can be just, if we wanted to adopt it, like you said, we'd need to make several changes, but it's not like a built-in. So thank you.
Yeah, like it was standalone also because we wanted to provide it like offline property, but IDE would allow that also, but submission tool probably will not allow offline usage. But yeah, there are in every like university there are of course like different requirements for how you want to use systems and that.
Yeah, thank you, Arupe, for the answer, because I see that William from our audience also asked the same question on IDE. Yeah, so thank you for your answer. Since Arupe, you mentioned like a lint, I actually have a question, The first question is, what is let me double check. So far, does the ASPA mainly focus on those coding style checks? Does it also include things like a null pointer dereference, that kind of traditional static analyzer functions?
Yes, it's more like a style checker, but and it currently works only on Python 3 because it uses Python's AST library and basically go through the abstract syntax tree and checks like different. There are like three types of or three violation categories. First one is like errors, which was in example, for example, global variable. Second one, like other fatal error in grading perspective would be if students don't use, for example, try except statements when using opening files or reading files and stuff like that. So these can be detected, and then if they then I think the second is like warning. If I remember correctly, if you left file open, so you are missing close method call, then that would be a warning. It's it's bad that you left it open, but program still may work. So it's a warning. But those which the severity level of those are configurable via JSON file, and then like example of this note is if student use if they because tool is for very novice programmers, also for non-CS majors. We have majority of our students are not CS majors, so they are from business and, for example, from chemistry, and because this is mandatory for almost every student in our university, so there are students who will never program after this course. So they will give. We have some style like things which are not. For example, we require that they use, or we recommend that they would use return command at the end of the function, even they would put return none. For example, like in my example, if it's missing, it's give a note that it's missing return, because for some students it's very hard to like understand when the function ends. And there are very simple, if they return constant string. Sometimes you maybe want to return a constant string, but for some students it's they are missing. They try to return a variable, but because they don't understand at the beginning the difference between variable and string, they put these the quote marks around the variable name and return the constant string, so it knows that you are returning constant string. And there are very basic checks, and then other ones maybe are more complicated.
That's actually really interesting, because that kind of a hint that you are returning a constant string reminds me from there's some work related to detecting misconceptions by tailoring test cases, and I think that's kind of really close to that one, but would be more kind of more generic, so that you would be able to kind of give feedback from some misconceptions, or likely some misconceptions. So yeah, thank you. You gave me some ideas.
Nice.
Yeah, I don't remember what was the like original question, but I.
Speaking about misconceptions, I want to mention one more interesting result. When we started to model semantic errors, determining them was not even the best results. What's the best result was that we were able to solve the tasks and determine the range of semantic errors that can be done. And this turned it out to be a good measure of what knowledge I need to solve a particular task or equation. So we're now working on generating questions automatically from mined program code. We can classify, and using that, and we just generated several thousands of questions, and our system knows when to use it. Trying to take the burden of creating a lot of exercises of questions from teachers. It's also important. but this requires automatic classifications. What kind of misconceptions can we do for each exercise?
Actually, a kind of a really short continuation to that one. Like, I think that all of us who have been creating kind of a test-based automated assessment thingies, so many cases we end up writing the test cases so that we kind of think about the corner cases and think about the misconceptions or whatever, and then we think about the feedback messages so that those would kind of tell something about the actual context like that, or kind of the likely reasons of that error message. And I think that all work that could kind of help automating that process, because that's tremendously tedious, like that that's specific to every exercise, and whenever you are creating automated tests to a new exercise, then you need to think about that, like how you could assess that specific exercise, right? I think all of this sounds really interesting.
Yeah, and also like Arupa even mentioned, students in his class may not have a lot of background knowledge in CS. They're not professional CS students. I think it's
And
quite
this is this is for the technical I told you before, the leading questions. When the student can't understand an error message, asking questions about this error, small pointed, often help. But it requires a lot of time from teachers, so it should be automated really. But it's one way to deal with poorly understood error messages. Start asking questions about the knowledge required to understand it. And
yeah, exactly. Yeah, that's
I
why we
have-
have this research direction for us to kind of tackle all those challenges for SE education. Definitely, Oleg, I completely agree with you.
Yeah, Carl, please see, I posted you the article. Did you find it in the chat?
Were you
Yep.
asking that to me?
Yeah, the article from Air Force Academy about robotics.
Oh, I haven't. Oh, yes, I said I will definitely give it a read. Thank you. And I just wanted to also kind of chime in because I've been listening to these conversations and reflecting on what we did during our course. And I think what's different is we were lucky to have so few students that we could spend a lot of time with them. But when I was thinking about these kind of automated tools that help students, what we did in our course was we had these kind of discussion periods where they would be working on something, and when they were done, they would come to us and we would discuss it with them. And this was really beneficial because the students that were doing really well, we could kind of tailor what we were doing to kind of extend their knowledge, and the students that were struggling, we could tailor it, like Oleg was saying, to ask questions. Rather than giving kind of a straight hint being like, put this line, we'd be like, well, what would you need to return in order for the next function to work properly, and things like that. So I think this idea of having kind of an automated questioning system really would be super useful for both learning and for learning.
Yeah. So Carl, I know that the class you present is super interesting, a higher level CS class, which requires knowledge on both robotic system and software engineering. So I wonder, would you recommend I want to use this class in Vanderbilt, for example, would you recommend any a prerequisite there for students who register for this class?
That's a very good question. We actually list that as one of our kind of, needs improving. Because this course draws from quite a few areas. Robotics
yes.
in itself draws from several areas, AI, control, hardware. So there's a whole kind of side there. And then software engineering has its own set of requirements, and we're trying to kind of put them together. So that is very tricky. I think when we designed the course, the goal was to make it kind of incremental in how we taught it, so that it wasn't like you needed to know everything. A lot of it was, we kind of built upon a step by step. So we're still trying to nail down the specific requirements, but I think we've designed it in such a way that we minimize, if they are missing a requirement, we've minimized the amount of kind of damage that does to their learning in a sense. And as well, because we're lucky to have such a kind of a smaller classes at the moment, we can, on the one-on-one sessions, help them when they get lost.
Yeah. So in your presentation, I realized you mentioned one of the biggest challenges is pairing the software engineering topics with the robotics topics. So I'm curious because apparently I just finished my class on the higher level software engineering class at Vanderbilt for undergrads. I realized almost for every higher level CS electives, we have this challenge because every time students work on a project, of course, it has its own theme, right? Machine learning, robotics. What are your suggestions or experience? What works well when you try to let students also practice a good software development process in their, like a theme specific projects? Like what works, what doesn't work? Like a teamwork, testing, like what do you think?
So, and what I'm going to state here is just from my experience. So, there's no empirical study proving what I'm about to say. But I think a lot of the things that we learn in software engineering, I mean, what we learn in software engineering is there to teach us how to make good code. And a lot of the times when we move over to other fields, we kind of drop that and we say, okay, well, we just need to get this to do that. And I'm not really worried about these good principles along the way. And so what we try to do in the labs and lectures, let me give you like a solid example. So in the one example, we'll have a lab where we'll say, okay, we need to design whatever it is so that the robot can do some task. And then either later on in that lab or later on, the next lab, we will reuse that code and say, okay, well, we need to reuse this code, plug it in and see how it works. And a lot of the times, if you haven't done your software engineering properly, that kind of process is very difficult, or you start to realize where you're missing things. So a lot of the times it'll be like this needs to be parameterizable because in the next lab, we're going to reuse it, but it needs to be configured slightly differently. So, that was just, one example. I think there are a few other examples, like I used that, the state example in another one where we're building states to help them kind of manage their code. So yeah, I hope I answered the question there. I also kind of I lost along the way, but I think the takeaway is that kind of emphasizing these good programming kind of techniques is really useful, and students get to see how it actually helps them when they develop these much larger systems.
So
Just go ahead, Alex. I'm often speaking about what we teach as teaching students to think, because it's not really about particularities of some language or some technique. It's about thinking consistently, open rules, knowing where to look and what to think, and learning to think often gets better than knowing some particular domain. And it's learning to reason, to think, to find conclusions, and to see what is good, what is bad. Not because the teachers say it so, but because they see the consequences.
That's true.
Otherwise.
Yeah, and usually when they're working on CS1 classes, the program's relatively small. Students may not realize, why do I need to do those, like a software development process practice? Then the higher level class, when they work on a big project, then realize, oh, that makes sense. Why do I need to, design my project well, documentation, all those kind of stuff.
Every kind of classes have its own problems. I also teach compiler design, and it's a very large project that has to be done in teams. And it's unlike CS1 certainly, but without good CS1, the people are simply helpless at compiler design.
Yep. Patrick, you were gonna say something.
Yeah, I was about to ask from Carl, like you said that you are kind of returning to old exercise and you are building on the previous exercises. And I was wondering, what are your experiences on or how does it work that is it so that all are able to kind of solve the previous exercises to that extent that they can actually build on that? Because in our larger classes with automated assessment, that's typically a problem if we are trying to build exercises that are building on previous exercises, that it might be that they have struggled too much with those.
Yeah, very good question. So the question being is, if they do assignment A and they don't complete it, and then assignment B is you have to build off A, and they haven't even finished A, how do they continue? So I think we kind of counted that in two ways in our class, and luckily, again, are a smaller class, so it's much more manageable. If we had 500 students or 1,000 students, I don't know if this is possible, but the two ways we handled it was, one, with these discussions, we we wanted at the end the students to have a completed version that worked, and we would kind of sit there and help them along the way. But there's obviously cases where that's just not possible. And in those cases, if they've just completely missed the deadline, what we would do is we would release the next lab that included kind of the solution to A. And this is beneficial in two ways. They can, build off of it, but they can also go back and say, oh, okay, that's how, it should have been implemented in the first place, and hopefully learn something from that.
Thank you.
Everyone, it has been such a great discussion in our session. So thank you so much, our presenters and our audience. I think it's about the time to end our session. I know you probably have other questions, for our presenters from our audience. So feel free to reach out to each other in the social room or emails. Yeah. So thank you so much, everyone. Yeah, I hope I can